Welcome to the deep dive. Okay, lots of you have been asking about the Poisson distribution.
Right.
It's this mathematical tool people use for understanding events. Seems random, but maybe not.
Exactly. It's about spotting the pattern, the hidden order in things that seem chaotic.
So our goal today is just to, get a clear handle on it, what it is, why it's useful. We've got your questions lined up.
Sounds good. Let's jump in.
Okay, first up, what kinds of events are we actually talking about? Where does Poisson really fit?
Well, the sweet spot is for events that are relatively rare and, importantly, independent.
Independent.
Yeah, meaning one event happening doesn't make another one more or less likely.
Yeah.
And they occur within some fixed interval. Could be time, could be space.
Like what? Give us an example.
Think website clicks per minute, or maybe radioactive decays in a sample over a second.
Mm-hmm.
Each click, each decay. It just happens. It's not triggered by the one before it.
Gotcha. Okay. Rare and independent within a set window. Now, how does this link up with the exponential distribution? I feel like I've heard them mentioned together.
Oh, they're very closely linked. You could say they're two sides of the same coin, really.
How so?
Poisson counts how many events happen in your interval. Exponential describes the time between those individual events. So as events are popping up according to a Poisson process, the waiting time until the next event,
yeah.
that follows an exponential distribution.
Interesting. Counting occurrences versus measuring the gaps. Okay. Now, mean and variance. I heard there's something special there.
There is. It's quite elegant, actually. For a Poisson distribution, the mean, that's the average number of events you expect.
Right.
And the variance, how spread out the counts are around that average, they are both equal to the same value.
Both.
Both. Equal to the rate parameter, lambda, the average rate they happen at.
So if you expect, say, 5 emails an hour on average, the variability in how many you actually get per hour is also related to that 5.
Precisely. The average dictates the spread. It's a key feature.
It makes sense. Now, what about approximating other distributions? Can we sometimes use Poisson as a sort of shortcut for binomial, maybe?
Yes,
Okay.
exactly. You can use Poisson to approximate the binomial distribution under specific conditions.
Which are?
When you have a really large number of trials, like lots and lots of opportunities for something to happen.
Okay.
But the probability of success on any single trial is tiny, very small.
Like finding a defect in a huge production run.
Perfect example.
Yeah.
Loads of items, trials, very low chance any one item is faulty. Success probability. The number of faulty items you find, often very well approximated by Poisson.
Right, lots of tiny chances adding up. Okay, what happens to the shape of the Poisson distribution as that average rate, lambda, increases? Does it change?
It does. When lambda is small, the distribution is quite skewed, piled up near zero. But as lambda gets larger,
Yeah.
it starts to spread out and become more symmetrical. It actually begins to look a lot like the normal distribution, that classic bell curve.
Okay, so it smooths out, becomes more normal looking with more frequent events. Good to know. Now, assumptions. What absolutely has to be true for us to confidently use a Poisson model?
Right, assumptions are critical. 3 main ones. First, events have to be independent, like we said.
Okay, independence check.
Second, the average rate of occurrence, lambda, must be constant over the period you're looking at. It can't be speeding up or slowing down within that interval.
Constant rate. Got it.
And third, 2 events cannot occur at the exact same instant. They have to be distinct points in time or space.
Right, they can happen close together, but not literally simultaneously.
Exactly. If those assumptions don't reasonably hold for your situation, then the Poisson model might not give you accurate results.
Important ground rules. Now, queuing theory waiting in lines. I know Poisson pops up there. How?
Oh, it's fundamental. It's often used to model the number of arrivals. Think customers walking up to a service counter or calls coming into a call center.
Oh, the arrivals.
Yeah. Assuming arrivals happen randomly but at a steady average rate, Poisson helps predict how many people or calls might show up in any given time period. That's step 1 for figuring out queue lengths, waiting times, all that stuff.
Helps explain why the coffee shop line is sometimes crazy and sometimes empty, even if the overall average is steady. Okay, so if I have data counts of something, how do I check if it actually looks Poisson?
Good question. You can do a goodness of fit test. Basically, you compare the frequencies you observed in your data, like how many times you saw 0 events, 1 event, 2 events, etc., with the frequencies you'd expect based on the Poisson formula for a certain lambda.
So observed versus expected.
Right. If they match up reasonably well, your data might follow a Poisson distribution. There are formal statistical tests, too, like the chi-squared test, to make it more rigorous.
Okay. And what if the data is messier than expected? Someone mentioned overdispersion.
Ah, yes, overdispersion. That happens when the variance in your data is actually larger than the mean.
But Poisson says they should be equal.
Exactly. So if your variance is way bigger than your mean, lambda, it's a red flag. It suggests the standard Poisson model might be too simple. Maybe events aren't truly independent, or the rate isn't really constant. There's some extra source of variability the basic model isn't capturing.
So the real world is throwing more randomness at you than the simple model expects. Understood. Lastly, the Poisson process itself. What is that, beyond just the distribution?
The Poisson process is kind of the underlying story, the mechanism that generates data following a Poisson distribution. It describes events occurring randomly and independently in time or space at a constant average rate.
So the distribution is the snapshot, the process is the movie.
That's a great way to put it, yeah. Think of traffic flow on a highway late at night, or maybe machine breakdowns in a factory, or even the arrival of emails. If they fit those assumptions, independent constant average rate, you can often model them as a Poisson process unfolding.
Okay, I think I'm getting it. Let's try to sort of unpack the key takeaways then.
Sure.
The Poisson distribution is super useful for modeling random-seeming events if they happen independently and at a roughly constant average rate.
Right, like those website hits or customer arrivals.
It's connected to the exponential distribution, which looks at the time between events, and its mean and variance are uniquely equal to that rate parameter, lambda.
Yep, that equality is a big clue.
And you've got to pay attention to those assumptions: independence, constant rate, no simultaneous events. Otherwise, things like overdispersion might show up.
Absolutely. The assumptions are key to knowing if the model fits reality.
Yeah.
It's all about finding that structure in what looks like randomness.
Precisely. So a final thought for you listening. Think about your own world. Are there seemingly random events, maybe errors popping up, customers arriving, even those moments of inspiration that might actually follow a pattern? Could looking through the Poisson lens give you a new perspective? Something to consider. Thanks for diving in with us today.